All right, today's lesson is on instantaneous slopes, or slopes of tangent lines. We can also call them derivatives. And we can also talk today about integration, which is the opposite. Let's start off with a graph, first of all, of displacement time. Let's say we launch a ball upwards in air. We'll ignore air resistance, so that it makes a parabola. Okay, so that we start with an initial velocity, we reach a maximum height, and go back down to the ground one more time. So this would be our displacement versus time graph. So what if I want the instantaneous velocity at any given point here? Well, velocity instantaneous, so I'll write velocity instantaneous. Okay, so V instant, okay, is equal to the limit of delta S over delta T as delta T approaches zero. And what does that physically represent? Well, when we look at it, if I pick three spaces on this graph here, let's say I pick a point located here, okay, and I'll put that in red, or no, let's put it in black here. So let's say I pick this point here about, and then one here, and one here. Well, when we look at average velocities, as we get closer and closer as time approaches zero, what we converge upon is the slope of the tangent line drawn to the curve at any given moment. So let's go ahead and draw that here. So we have the slope of a tangent line drawn to the curve about right here would be some kind of a positive slope. The slope drawn here is going to equal zero, and then the slope of the tangent line here is going to be equal to a negative. So we have three instantaneous slopes. Now, what does that correlate to our velocity time graph? Well, we can estimate where those might be located. So our velocity right there would be about right here. And then maybe down right here would be the zero, and then maybe down here would be the last one. And we're going to get a straight line graph because what we have is a constant acceleration due to gravity, okay, as we go up and all the way around, and we'll have a straight line graph going downwards, okay? So that's how we would graph our instantaneous velocity. So essentially, the velocity time graph is a graph of all the slopes of all the tangent lines as this thing goes all the way around. And we start with a positive value and then go to zero and then keep going negative, negative. Of course, we have a definite end here, okay, where we reach the ground again. Okay, now let's look at our acceleration versus time graph. Well, if I want acceleration instant, that'll equal the limit of delta V over delta T as delta T approaches zero. So what that means, well, I'll again draw tangent lines of the curve here. Well, if we look at this, there's all the tangent lines would line up on, right on this graph itself, right? So we have one constant value for that. There's only one constant value. Okay, and that would be the acceleration due to gravity. Now I'm going to write that as -10 today to make it easy for us to solve questions on this. -10 meters per second squared. Okay, so that's how we get our instantaneous velocity and acceleration. Of course, this graph is all the slopes of tangent lines drawn to the velocity time curve, and it's one value constantly all the time. All right, now let's put some values to this. Let's say we're starting at 0 time, and then we go to 2 seconds, and then we go to 4 seconds, okay, from this part of the line, okay, all the way down there. And let's say our initial velocity upwards is 20 meters per second. Okay, and then 4 seconds later, of course, down here would be negative 20 meters per second. So we have actual values here. And again, this is our 0 point here, and this would be our 2 point here, and this would be our 4 point here. And that's for our time values. Okay, so let's say we start with the acceleration time graph. We want to go backwards to figure out our change in velocity. Well, now that's going to be the integral. So what we've done first is take limits, or derivative, which is the same thing as slopes tangent lines. What if I wanted to go backwards and find my change in velocity? Well, let's put our time values on here again. So we have 0 seconds, okay, we have 2 seconds, and then we have 4 seconds. Okay, to get the integral, or take the opposite of it. We're going to take the area under the curve. Try to draw that line straight. Okay, so it's this area under the curve here. And what do we have? Well, we have a rectangle whose dimensions are this length times this width, right? So the area under this curve is going to equal, okay, a negative 10, and that's meters per second squared, times by 4 seconds. And what's going to happen here is meter per second squared times a second is indeed going to cross off one of the seconds. And we're going to be left with the area of this equaling negative 40 meters per second. So we're going to get units of velocity. Because I took a meter per second squared and multiplied it by a second time. We're going to lose one of our seconds here, okay, and be left with meters per second. So when I take the area under the curve, I'm now finding the velocity change that occurred in this part right here. So let's take a look at that. So that's the area under the curve. Negative 40 meters per second is my change. So if I look at this, I'm negative 20 meters per second here. And if I subtract 20 meters per second for that, my change in velocity for this graph indeed is negative 40 meters per second. That would be the change in velocity for that. So by taking the area under this curve, we can calculate the change in velocity for this curve here. It's called taking the integral, or finding the area under the curve. Okay, now what about going backwards one more time to get the area under this curve to find the total change in displacement for our graph here? Well, what we do there is we've got an area here and an area here. Notice how it's always bound by the x-axis. So I'm calculating the area bound by the x-axis in both cases. This is a rectangle bound by the x. We got two triangles bound by the x. Well, let me find the area there. Area there is going to be 1/2 base times height. So 1/2 my base looks like it's 2 seconds. I'm going to put my unit there too. And my height here is 20 meters per second. And what's that going to do? Well, that is going to cross off seconds. And I'm going to say 1/2 of 2 is 1, okay, times 20. That's going to then be 20 meters. So the area of this triangle here, okay, is going to be 20 meters. Notice how we get meters units because we cross out both seconds. Now if you look at this triangle here, I have a 2 this way and a negative 20 this way. So I got to add plus 1/2 of 2 seconds. Now I'm going to have to multiply that by negative 20. Okay, and that's going to get me a negative 20 meters. 20 meters plus a negative 20 meters is going to give me 0 meters of total change of displacement for this graph. I go here, I notice I start at 0, I go up, and I come back down and end at 0. So we see that the total change in displacement here is 0 minus 0, which equals 0. My beginning displacement was 0, my final displacement is 0. So that's integration and the derivative. We take derivatives, or slopes of tangent lines, to go from displacement time to velocity time, and likewise from velocity time to acceleration time. If I want to go backwards, I've got to take the area under the curve to get velocity, and take the area under the curve to get displacement. But what we're getting, guys, is change in velocity. So this is my change in velocity, this is my change in displacement. If I don't know my beginning displacement or my beginning velocities, I would only know the changes. I won't know the actual velocity we're traveling at any given time, or my displacement at any given time. But please remember, when we do experiments, if you look at what's going on, you're going to know what your beginning displacement is, and you'll know what your beginning velocities are. So you would just record those and add the changes. So what does that mean? So I look at this. If I know my change in velocity is negative 40 meters per second, but I didn't know my beginning was 20 meters per second, okay, then all I could get is my change, and I would never know exactly what velocity I was going at any given time. But since we do know our beginning velocity and we know our change, we can easily know what our final velocity is. And likewise here, we know our change in displacement, but we know we started at 0, And we have to end at 0 because I know where my starting position is. So that's how we do integration, okay, and finding slopes for tangent lines.